Good afternoon, everyone. This is our beginning to chapter 9 for Intro to Statistics. Today, we're going to cover confidence intervals for population proportions and means. This is sections 9.1 and 9.2. They're very similar. And so let's take a look at what's going on. What is chapter 9 about in general? Chapter 9 is on inferential statistics. This is when we start beginning to make inferences. And inferential statistics is the process of trying to infer something about the general population given data that is collected from a sample. When we infer something, inferring means making an assumption. Okay. So I'm going to start off, I want to talk about the coronavirus and what's going on right now. We don't actually know its mortality rate. We keep inferring a lot about what its mortality rate is based on different samples. So I wanted to look at a couple samples with you and see what we could decide. So this was I'm pulling data from the current report. You'll notice this is based as of today, March 29th, 2020. And I'm just going to jot down some numbers that I see here. Let's look at California. So we'll look at confirmed versus death. Now I realize that there's a time delay between being confirmed with the virus and dying. And so when we compare ourselves to the global thing, it's not the best comparison, but we can take a look at what's going on. Let's look at California. Let's look at New York. I'm making a table real quick, but I want you to see where it's coming from. California has 5,551 confirmed cases, which you'll see on my page in a second. And the number of deaths right now are 101. If I scroll down, we see Michigan has a high number too, but who's got the big number? New York and New Jersey. Let's take a look at them. Those are the biggest other two. New York's got 59,513 cases with 965 deaths. And New Jersey is 13,386 with 161 deaths. If we're trying to infer something about the overall state of what's going on, we can make something called a point estimate. And so I'm going to do that here. Our point estimate is p hat. And it's successes over total. And if we're looking at the number of deaths as a proportion of the population, we're gonna, which sounds a little morbid, we're gonna consider deaths a success. So for here, I'll write the fractions for each. Here I've got 101 over 5,551. Here I've got 965 over 59,513. And here's 161 over 13,386. We can figure out these actual values as a decimal if we put them in a calculator. 101 divided by 5551, 0.01819, or 1.819%. And I'll look at the other two. 965 divided by 59,513. 0.0162 or 1.621%. And if we look at New Jersey's, $161 divided by 13,386. Or 1.203%. Notice each of these is different. That's why they're called point estimates. It's not guaranteed to be the overall proportion. In fact, if we look at global values, as I'll do on the next page, global values today, 33,903 deaths out of 720,217 total confirmed cases. (0.04707) or 4.707%. Now, looking at these figures, it looks like the United States values are much lower than the rest of the world. But a lot of the rest of the world's had it for a longer period of time, and it's had more time for people to die. We won't really know until this is all said and done, really what the true case is. The point is, and pause if you need these values real quick. Okay. I'm going to use one of those values in a second. Each sample had a different proportion as a point estimate. Interestingly enough, in California, we had the worst percentage amongst the 3 states I looked at. But checking with a different group, different sample yields a different percentage or proportion. Now, I could ask a whole bunch of groups and sample a whole bunch of states and try to figure out what the proportion might be. Let's get rid of that gloomy statistic. But maybe it's just better to say, can we come up with an interval that likely contains the true proportion for the overall population. It's funny because I wrote global down up above, but we're not done with this pandemic. Chances are when the final shindig's done and over with, it's going to be somewhere near that 4.7%, above or below. It might be some countries didn't have as rapid responses as we have. It might be we just haven't caught up to the death curve yet. And I bet if we looked at different countries that have had it for a while, like Italy and China, we would see different percentages amongst the countries. But there is likely a range of proportions that contains the true value. So what if I say it's between 0.01 and 0.08, or 1% to 8% death rate. How confident am I with those numbers? Well, if I said 0% to 50%, I would probably say I'm 100% confident it's in that range. If I say it's between 1.6% and 2.2%, I may not be very confident at all. I might only be 10% confident. I'm just generating numbers right now. We will show how to come up with these numbers statistically. The point is, the narrower this range, the narrower the range, the less confident I am that it has the real proportion. Like it might be 2.3 or 1.5. And so like anything that's above 2.2 or below 1.6, I'm outside of this range. And so this proportion range missed, this interval missed, but 0% to 50%, all those numbers were in there. So that's the idea of what we're doing here. And the wider the range, the more confident. Pause and let you jot that down. Okay. Now in statistics, this is what we do in statistics. In statistics, we want a specific confidence level. And a confidence level is a percentage level of confidence. How confident are we that our answer contains the right piece of information? We want this to be high. But if we make it too high, we narrow the range, we make the range too wide, and it just becomes less useful. These are proportions, and our rules of proportions still apply. This is a proportion, our p hat. And for proportions, we still need the following rules to apply. We need n times p times 1 minus p. And in this case, we're using p hat to be greater than or equal to 10. And I need n to be less than or equal to 5% of the population. Let's take a look at California's numbers. Let's use California's. For California, the death proportion, this is gloomy. Maybe I should have focused on recoveries. The death proportion p hat was 0.01819. N was 5,551. So we can check this. 5,551 times our p hat times 1 minus our p hat. Is that greater than or equal to 10? Let's check. 5,551 times 0.01819 times parentheses 1 minus, oops, that's plus, minus 0.01819 and parentheses equals 99. 99.14 is definitely greater than or equal to 10. I meet that requirement. And this is definitely less than 5% of California's population. With those in play, our stuff approximately follows the normal distribution. But I want to illustrate to you a little bit better what I mean by this confidence interval thing. Because when I say it includes the correct value or not, that's a little confusing because we don't know what the correct value is. All we can do is set our criteria such that when we calculate out a range, and we will calculate a range, we're not just going to guess numbers like I did here. I guessed numbers to give an example, like the 1% to 8%. We're actually going to work it out. Let's take a look at how it works in StatCrunch. StatCrunch has an applet that we can look at confidence intervals, and I'll do a proportion. And right now, my p hat is what I'm going to stick in for the proportion. I'm going to plug in 0.01819. And I asked 5,551 confirmed patients how many died. Oh, wow, that's hard to read. This is not good. Can I zoom in? Let's lower the sample size down to 100. 100 is easier to understand. And I'll make the window smaller. So this is the proportion that we're looking at. We think that's what the value is. That's what we're basing it on. And so we're going to do 100 samples, or it's going to calculate 100 samples that have 100 people in each sample. Again, that's kind of funny looking. Let's try this again. Let's go with 50. This is too low a proportion to work with. It doesn't like doing it. This is a... let's use the global proportion. The global proportion was 4.707%. Let's try that. We'll just ask 30 people, 40 people. What it's going through is it's simulating each one of these lines. It's simulating what happened. How many actually had it? If I look at sample number 94, 2 people out of 40 died. The sample proportion is 5%. If I look at sample 93, no one died. And this was outside of our values. I'm going to change this. This is not working. I thought this would be good because it uses current stuff. Let's do a more realistic or easier to work with to illustrate at least. Illustrate this with Snapchat users. So let me shrink this down for a second. Let's illustrate this with Snapchat users. And let's say we asked 250 students and 150 said they use it. My p hat is going to be 150 over 250, which is 0.6. Values in the middle are a little bit easier to illustrate. Let's go with 0.6. 250 people asked. And so this is what it means. When I say I'm 90, notice that it says the initial confidence level is 95% or 0.95. So the applet, I'm doing 0.95 confidence level, which translates to 95%. I'm using p equals 0.6, and I'm using an initial sample size of 250. Let's see what happens when I click compute now. So notice each of these lines has a certain width. Notice all of the red lines don't touch this central line. This black line right here is the 0.6 line. Any of these that have a red line, like sample 86, which is probably right around here, it has a value where our sample, we said it's 0.6. We think it's 0.6 based on our proportion. It does not lie within their 95% limits. If I look at a green line, 0.6 lies between 0.53 and 0.65. So let me jot these down. Line 86, let me click on it again. Line 86 said a lower limit of 0.458 and an upper limit of 0.582. And it was a red line. I'll look at line 89, and I know you can't see what I'm writing right now. I want to keep this up where you can see it. Line 89, I'm looking at these two values. 0.531 and an upper limit of 0.653. Notice it says the sample proportion is 0.592. That's the p-hat for that sample. 148 out of 250 is 0.592. This one said a sample proportion of 0.52. So let me illustrate pictorially what's going on here. So we found out that we had the values where this was going to follow an approximately a normal bell curve. My normal bell curve I had a p-hat of 0.6. And my other two, I have a 0.592. I'll say 0.59. And I gotta move this way out here to put 0.52 down. Each of these has its own bell curve. And that 95%, if you recall, it corresponds to 2 deviations. So what this is showing is on my 0.6, this is my black line right here. When I go out 2 deviations, this is my 95% interval. 2 deviations, approximately. The 0.52 lies outside of it, but the 0.59 lies inside. And if we look at this, how many actually said that? This sample, the overall thing, I had P equaled 0.93. I'm grabbing this from the upper corner. This means that there are 7 samples, 7 red lines that did not contain the 0.6. And there were 93 lines, all of them green, that contained the 0.6. That's what's going on there. That's the idea of the confidence interval. So when we look at different samples, I didn't want to shrink it all the way down. Resize it. There we go. When we look at different samples, some samples are going to contain the true characteristic or true value, and some are not. Right now, the global value says 4.7%, and New Jersey showed 1.2%. If we look at other states, it was even lower. Some of them have values that they just don't, they're not matching the true value, and some of them do. That's kind of what's going on here. Let me be try to be a little bit more specific. Let's look at that 0.6. When we say we are being 95% confident, we're saying 95% of the solutions will contain the data, or 95 out of 100 will contain the value 95 samples out of 100 will likely contain the value, contain the true p hat. The empirical rule said, when we did it, we said this was p hat plus 2 sigma, and this was p hat minus 2 sigma when we wanted 95%. But that was round, we did some rounding there. And the reason why is 2 is a heck of a lot easier to remember than the actual value. If we want the actual value, 95% actually lies within plus or minus 1.96 deviations. If I want to go 90%, my block has got to get smaller, which means I'm going to be less deviations out. This ends up being plus or minus 1.645 sigma. And we actually saw that in chapter 7, right before we were doing the midterm, when we were looking at calculating the z-scores, and I gave you values that were what was within 2 deviations of the IQ score. I actually chose something that was 1.645 deviations away. And if we want 99%, we need to capture more of the data. And this ends up being plus or minus 2.575 sigma. Ooh, phone's vibrating the whole table. So what does this mean? These are important values to have. They are going to ask you for stuff like this in the homework. So what I was saying about the samples, I'm going to write down a sentence that has that in words. A 95% confidence interval says, or means, if we do 100 samples, approximately 95 will contain the true proportion. And 5 will not. Notice when I did that here, I had 93 that contained it, 7 did not. But if I do the same thing again, just recompute it, get a different 100 samples, well, now it still looks like maybe 7. Let's take a look. This had 92 samples that had it. If I add another 1,000 intervals though, the more intervals I do, the closer this gets to 0.95. So right now I have 10,100 samples, 9,552 contained the 0.6 that I said was the correct value, which is 94.57. That's the idea of what's going on there. So how is this done mathematically? What is StatCrunch doing here? How do we actually do this? How is this calculated? Well, what StatCrunch is doing is it's finding the average P, or the mean P, and that's going to be our P hat. We did this in chapter 7, remember? Or 8. Sigma P hat was P times 1 minus P over N. For the example we just did, mu P hat was 0.6. Sigma P hat, my N was 250. So this is 0.6 times 1 minus 0.6 all over 250. And then we take the square root. If you do that, you get 0.0310. So depending on your proportion and your N, you will either calculate, if you're doing this by hand, if you're a crazy person, or StatCrunch will calculate this for you. It'll calculate the mean and standard deviation for this normal distribution. We needed it to be normal, and that's why we did the N times P times 1 minus P. So let's take a look at how that bell curve works now. Let's do 95%. That goes out so far. 95% goes out plus or minus 1.96 sigma, which means from P hat, this is P hat minus 1.96 sigma. And we have values for these. We just calculated them. So I'll do the one for P hat over here. P hat minus 1.96 sigma is 0.6 minus 1.96 times 0.0310. And I get 0.0607. That'll be my 95% or lower bound rate. And if I do plus, .6 plus 1.96 times 0.0310, this is about 0.6607. And this is our P hat plus 1.96 sigma. And what we'll say, we were talking about Snapchat here. So we are 95% confident. That's what we just calculated, 95%. We are 95% confident that the true proportion of Snapchat users is between, that value looks funny, This should be 0.59 or 5393. .96 sigma was 0.0607. Is between 0.5393 and 0.6607. Now, this is assuming I asked 250 people and 150 people said yes. In an actual test, you will survey a certain number of people, and some of them will say yes and some of them will say no. Like we have with our data for the death rate for coronavirus victims. Some have died, many have not. Can we do this with our coronavirus for California? Let's take a look at it. Let me pull up that data again. For California coronavirus. I had p hat was 0.01819 and n was 5,551. We already showed earlier n times p hat times 1 minus p hat was greater than or equal to 10. We already showed that. So let's jump to calculating the mean and standard deviation. Our mean is just p hat. Our standard deviation for p hat, I've got 0.01819, that's p hat, times 1 minus that, all divided by n, and then we take the square root. I don't think this number is going to be very big. 0.01819 times parentheses 1 minus 0.01819. I'll divide that by 5,551. And now I'll take the square root of the answer. Zero, I gotta shift the decimal place 3 times. 7936. We'll go 937 to 5 significant digits. Let me do the P again. Maybe I can get that a little bit tighter. 1819, let's add a 5 to it. So if we want to do the bell curve here and generate a 95% confidence interval, our p hat goes in the middle. If I want 95% confidence, I need 1.96 times that sigma. All right, times 1.96 is 0.00351556. And let's calculate what p hat plus that is and minus that. P hat minus that 0.018195 minus answer. And if I do plus it, it's not a very big range. These numbers have not separated that much. This is 0.014. This is 0.02. If I go to 3 decimal places, 22. This is 2.2%, 1.8%, 1.4%. 95% of the samples we conduct should have that the value in there. 5% won't have it. Sometimes your sample is just wrong. Our sample might be too high, it might be too low. If it's actually according to the global thing, it sounds like we're not high enough yet. That's the idea of what's going on with these confidence intervals. And so based on our data, what would I say here? We make the same statement every time. Or very similar to statement every time. Based on whatever percentage that we're using, we are 95% confident that the death proportion among coronavirus victims is between 0.01468 and 0.02171. We say we're 95% confident, and the best part about it is there's a chance we're wrong. And there's really no way of knowing with your given sample unless you know the overall population's real proportion. And that's why it's a confidence interval. It could be wrong. A lot of mathematicians don't like statistics because mathematics is accurate and exact. And statistics, we don't know for certain whether we have the right answer or not. Our proportion range may not contain the true proportion. And to illustrate a couple more ideas. So we had 95% right here. If I want to have a higher confidence interval, I need to capture more area. Let's say this does 99%. The interval has to widen. %, it's narrower. Now, the real kicker is, and this is what I mean by it, what I was saying a little bit ago. The true parameter is a fixed value. So it has to be somewhere. If our interval contains it, it's a normal sample. If it doesn't contain the true proportion or true parameter, then we are in the outside 5%. Which means our sample is unusual. And it's really, if you have two samples that are completely different, it's really hard to decide. Let's look at some more information for this. Kind of wish I hadn't used coronavirus. I didn't try working out the numbers ahead of time. I thought it was a perfect example since it's current and it's on everyone's mind because it's affected the entire country and world right now. It's a good example. It screwed up my applet though, and I don't like that too much. Let me go back to my Snapchat scenario to explain something a little bit more. So my Snapchat scenario, and I made up those numbers, 150 out of 250. We could survey and ask. So I made my interval by adding and subtracting 1.96 sigma, which equaled 0.0607. So we call the lower limit the lower value. And that was 0.5393. The upper limit is the top part of our 95%. Of course, this is our p hat. This is our point estimate. So I have this range here where I got 0.5393, and I'm going up to 0.6607. Halfway in between is p hat, is 0.6. This distance left and right, I added and subtracted 0607. This 0.0607 is called the margin of error. So it's really our confidence interval goes from p hat minus the error up to p hat plus the error. So let's call that E. And the reason why we do it was we don't think our p hat is exact. So we use this range around our p hat so that we include more values and say we likely have the real value now. So the margin of error is used because p hat is likely to be inaccurate. But close. And by extending the margin of error either direction, error amount in both directions, we likely capture the true parameter. Another piece of info for you, if we have this little number line, I've got p hat in the middle, I've got p hat minus e over here, and I've got p hat plus e over here. That means this distance is e, this distance is e, and they call the distance from p minus e to p plus e, this is called the width. The width equals 2 times the margin of error. Okay, that's what's going on with confidence intervals. How can we do this in StatCrunch? Let me let you finish writing that down. Wet my whistle. I'm drinking a lemon zest tea. It's cooled down a little bit. Been really enjoying a peach tea. Celestial Seasonings Peach Passion. Oh my gosh, it's so good. Nice hot tea during the cold weather. A lot of people aren't feeling well. Rocking. All right, so StatCrunch. Hopefully you got an idea of the what a confidence interval is. We have stats. We're going to go proportion stats. And at this point, we have a couple options. We can do 1 sample or 2 sample. 2 sample is going to come up later on. It's a later chapter. 1 sample is right now. Then it asks us, do we have data? With data as an option. This is for either of these. With data, we need a table column of information of info, like yes or no, Republican or Democrat, success or not. Remember, this is qualitative data. With summary, this is when you have the results already organized. And that was how it was for both of our examples, both Snapchat and the coronavirus. This is what we had. And in these cases, we're using p hat is x over n. We need to know the successes. We need to know the total sample size. There is one more option in here. I'm going to show you how it's used. It's called power sample size. I've got 4 examples I want to walk through with you on 9.1. We're going to use power sample size This is for finding the sample size needed to yield a good interval. Sometimes you have an idea of what the percentage is, and you just need to know how many people do I got to ask before this is a normal distribution. We're aiming for a normal distribution is the goal. Because when we have that, we can do that bell curve. We can do the 95%, and all those numbers I gave you apply. And again, we need n times p hat times 1 minus p hat need to be greater than or equal to 10, and n needs to be less than or equal to 0.05 n. And I'm going to look at in 9.1, I want to take a look at problems 1, 2, 3, and 6. That'll get your feet wet, get you started so you can see how this stuff works. I'll leave that up a little bit longer. This is what we're going to use. Okay. Do this. It's making my screen too big to have it down where I had it. I do want to point out something else to you here. Those of you that are missing it, let's just take a look at it, because these are valuable resources. This multimedia library section here, when it loads, rude. Come on, load. Let me log out and come back in. Oh, yep. I was completely logged out. And they're having technical issues right now. I might have to come back and do videos on this in a second, but let's see. Let's try to get in. Let's see what's happening. Please work. Let's just try looking at this. Oh, was it going? Dirty trick. All right. I might have to come back and do videos on how to do the problems in a second. I'll check it before we're done. Let's take a look at 9.2's info. We'll come back to this. If I have to make a separate video, I will. So hopefully at the end of this video, but maybe second video. All right, so let's take a look at, is it gonna work yet? All right. 9.2. 9.2 is doing something similar. Here we're going to estimate a population mean. And recall in 9.1 we did population proportion. And what we needed in the population proportion is similar to what we need in the population means. Here we needed mu of p hat and sigma of p hat. For 9.2, we need mu of the sample mean and sigma of the sample mean. Now, it just so happens, if you recall, when we did this before, chapter 8, the mean was just the mean, or X bar. And when we calculated sigma, we had to have the standard deviation of the population, and we divided by the square root of n. So in 9.2, our point estimate is X bar. And to complete our inference, of the overall population, we need the standard deviation of the overall population. And that's what we need. If we want to do this the same way we did 9.1, using the formulas that we did from chapter 8, this is what we need. But if we stop and think about it, I use red. If we have sigma pop, we probably already have mu. It's kind of hard to come up with have the population mean mu. It's hard to come up with the standard deviation without the mean. So we don't have sigma pop. Which caused quite a dilemma. So I'll let you finish writing that. All right. I'm assuming you hit pause if you needed to. So we don't have it, and there's this guy. True story. I'm not making this up. There's this guy. Named Gossett. That's his last name, I believe. And this was back in the early 1900s. and he works for Guinness Brewery. He's a beer maker. He's not the owner, but he works with the beer brewing industry. He's a beer sampler. He was trying to infer something about beer in general. Based on sample data, just like we're trying to do right now. Just as we are. But there's no formula he can use. There's nothing that's going on. So what does he do? He just collects data, and he keeps collecting data. He collects a shitload of data. He does different sample sizes. And he does so much that he is able to develop a table that substitutes for sigma population. So that's where we're at. He's working in beer brewing industry. He's trying to make an inference about the overall beer industry. He just collects a shit ton of data. He does different sample sizes, different things of that, different batches, stuff like that. And he ends up coming with this table. But guess what? Guinness won't let him publish it. Won't let him publish under his own name. So he adopts a pseudonym. Oh, shoot. Pseudonym. I don't know if that's right. Pseudonym? Oh, now I'm curious. I'll have to look that up in a second. His name that he goes by is Student. And instead of using T, or instead of using sigma, he uses T. And ultimately, this yields us Student's T distribution. Rude. All right. I hope you hit pause. So let's look at the properties of the T distribution. All right, well, first off, T is symmetric. Bell-shaped. And centered at 0. Like mu equals 0. Just like the standard normal distribution. Number 2, T is different for different sample sizes. Number 3, because it's symmetric, the area to the left of 0 or right of 0 has to equal 0.5. So there's a lot of properties that are very similar to the standard normal distribution. Number 4, the tails approach but never touch 0. Never touch the number line. Which would mean they equal 0 if they do. Even for the most extreme values, there's a possibility. It may be completely improbable with so many zeros after the decimal point that you have a better chance of getting struck by lightning 10 times in a row, but it's still possible. Compared to Z, or the normal distribution, the tails are longer for T than Z. What this means is for the same amount of deviations, for equal sigma, T has more area under the curve than Z. Has more area under the curve than Z. It's spread out wider. Please hit pause and finish writing it. There's a reason for this. So our parameter, sigma, is for the population. And our statistic S is our sample deviation. And the reason why it's greater, the area is greater because sample standard deviation or sample deviation is going to always be bigger than the population's deviation. Is larger. But rule number 6, as the sample size n increases, S gets closer in value to sigma. And they become better aligned or closer aligned to Z. Now we had some requirements on N and P for population proportion. We have some requirements here. Requirements for a confidence interval. And I'm going to abbreviate that CI. Requirements for a confidence interval for a population mean is, remember, we want a normal distribution. We have two ways of getting this. The easiest one, if n is greater than or equal to 30, the central limit theorem kicks in. And we have a bell shape. That's the easy one. You just have to have a big enough sample size. Straightforward. I'll let you pause and finish writing that. Okay, the other option, if n is less than 30, we want two things to happen. We want the probability plot which in StatCrunch is our QQ plot, to look approximately linear. And to be more specific, when we do it, we can add correlation statistic, and that's what we want to do. Add correlation to statistic. The graph actually looks better if we do normal quantiles on y-axis. And this is going to give us, at the top of our chart, graph has correlation statistic at top. We then have to look at a critical value table. Which is based on sample size. I'm going to call that CV. And I'm pretty sure they call the correlation stat R. Then we've done this before. This was in section 4.1 and 4.2. Doesn't come up a whole lot because oftentimes when we're doing problems, it will tell us it's normally distributed and we don't have to worry about anything. If the problem tells you it's normally distributed, you're good to go. Here we check, is R greater than CV? If the correlation statistic is larger than the critical value, it's approximately normal. That's part one. That has to happen. If n is less than 30, we need that to happen. And we also want to make sure a box plot yields no outliers. Ready for more info? Okay, so if you see T hat or T alpha, it's like Z alpha. T alpha is the value of T such that the area to the right of it equals alpha. T of 0.10, you do it where it's just enough that this area equals 0.1. Okay, for this, we're going to do stats, T stats, calculator. Oop. Stats, T stats, one sample or two sample, just like we had before with the proportion. And it's also going to have a third option called paired. One sample, this is in chapter 11. Two sample and paired is chapter 12. So this is when we're looking for the area. If we want to calculate t, we're going to do stats, calculators, t. So there's two options. This is what you're going to do to find a specific t based on data. And this is what we're going to do if we want a confidence interval or a hypothesis test. We're going to do stats, t-stats, one sample, two sample, or paired. The t calculator requires degrees of freedom. And if you recall, we've looked at that before. Degrees of freedom is n-1. Now I have StatCrunch open, so I might actually be able to go through some of this without having a specific problem set up, because I've got a couple of problems set up. So let's do some with the mean, and then we'll go back and see what's available to look at in the homework. I might have to make a separate video for the homework when MATLAB is being friendlier. So problem A, find the t-value such that the area to the right is 0.2, assuming 10 degrees of freedom. All right, so here we're looking for a t-value. This is where we're going to do stats, calculators, t. T. Ten degrees of freedom is the default. DF is degrees of freedom. Notice that the red is showing me what side it's currently looking at. I want it to be on the right side, so I'm going to say greater than or equal to. To do this, I'm going to say DF equals 10, and then probability that X is greater than or equal to something equals 0.2. I'm going to change this right side to 0.2. Notice that blanks this out right here. And when I click compute, it gives me the value. To 4 decimal places, 8791. When you're using the t calculator, I don't know why they don't put in t, because they actually call this the t calculator. This is saying t equals 0.8791. That's just sloppy programming right there. Okay, why don't you guys try? Area to the right is 0.27 and n equals 20. I'll give you a moment to try that. Okay, what should I enter here? What should I do with the 20? Well, this is what I was being sneaky right here. I don't know if you caught this. I gave you n. Degrees of freedom is n minus 1. 20 minus 1 is 19. So I'll change my degrees of freedom to 19. And then I'm going to say probability that x is greater than or equal to blank equals 0.27. It clears out the middle until I click compute, and it gives me the value 0.6241. So t equals 0.6241. Okay, I'm going to give you some more data. I'm going to give you a data set. I actually had it loaded already. But this next problem, you should try doing this on your own when you have StatCrunch available. Construct a 99% confidence interval for the population mean weight of pennies minted after 1982. And this is my data set. And it's in grams. I have 2.46, 2.47, 2.47, 2.45. You're going to want to enter these all in one column, but I don't want to take up the whole page, so I'm going to do it like this. I'm going to make 4 columns. Okay, that's my data set. I've got 4 in this column, 4 in this column, 4 in this column, 5 in this column. N equals 17 here. You're going to want to pause that so you can enter that all into StatCrunch. I'm going to check my values, make sure they look good. Okay, those are my values. I'm going to go stats, t-stats. I've got one sample and I've got the data. So let's show that again. Stats, T-stats, one sample with data. Have your data in one column. Tell it where that data is. Later on, we're going to do hypothesis testing. Notice it tells you what parameter we're looking at. We're looking at the mean right now. When we look at proportion stats, it's going to say P there. I want a confidence interval, and it says 99%. I want to change that to be 0.99. So this is what StatCrunch spits out. Notice it tells me my sample mean. It tells me my standard error, 0.0042925057. That's actually my S. It tells me my degrees of freedom, which we already knew. And -1, 17 minus 1 was 16. And then it gives two pieces of clutch information. Lower limit, 2.4516. I'll do the 4 decimal places. Upper limit is 2.4767 to 4 decimal places. And what we want to say, we're going to make a statement of confidence. So pause out if you need that data up longer. Hopefully you're running this in StatCrunch as you do it yourself. We're going to use our lower limit and upper limit. We were looking at 99% confidence. Notice it tells me that right here. It tells me what confidence interval I was looking at, 99%. We are 99% confident that the mean weight of pennies, I'm paraphrasing what was in the initial question, the mean weight of pennies minted after 1992 or 1982 is between 2.4516 grams and 2.4767 grams. It's actually a pretty tight margin there, if you ask me. That's how we make statements of confidence. Okay, please, please, please be up and running, StatCrunch. Let's try a different class. That page loads. Can I load the multimedia library section like I want to? Maybe managing view as a teacher will help. Check the third class real quick. Okay, so I'm gonna have to do another video in a little bit. It might be later tonight. I'll try again tonight. I do want to say for stats, we've caught up for chapters 8 and 9 in videos. Videos are created. I did 9.3 a little bit ago. I haven't posted it yet. 9.3, what it's doing is it's looking at, we've looked at population proportion and population mean. When they give us just a generic problem, what one are we looking at? And I'm going to give you some strategies for how to look at it. It's a second video. It's much shorter. Just how to pick between them. And it's actually a good summary video on what you want to do. So chapter 8 and 9 videos are posted, are created. I'll post them as soon as this is done. Starting this week, during normal class hours, I am going to have a Zoom conference open. That's the program I'm using right now. You can find it in Canvas on the bar on the left, and I'll show you right now. I actually have meetings for my trigonometry class already set up. I haven't set up your guys' classes, so I'm going to show you what I see when I go to it. Yours is going to be in the same location. You're going to scroll down and you're going to look for Confer Zoom. And I'll write this down in a second. Confer Zoom is right there. Click on it. I wonder if I can see, view as a student. Let's see what a student sees. For them, they can see I have 2 appointments set up. They have classes on Monday and Wednesday from 4 to 6. I have Zoom conferences set up on those days. Just come here right before the start of class, click on it. You don't need to have video, your own video camera running if you don't want to post anything. You can just put a picture up if you want. If you have video running and audio running, you can ask me questions and stuff like that. Come to StatCrunch and, oops, not what I wanted. I want to get that, there we go. So click on the link. And what I'm going to do with class time is going to be for Q&A. I've already made videos on chapters 8 and 9. I'm going to work on videos for chapter 10 this week. Okay. So class time is going to be for Q&A. Watch the lecture videos and try some problems. Try the homework. Then you'll know what to ask me when you get to the Q&A. The reason why I'm not doing lectures in the Q and in the normal class hours is because with all that's going on with shelter in place, people trying to work and kids are at home and stuff like that, a lot of people are not going to be able to log in during those hours. And I don't want to have to lecture on the same topic 8 times. I'll run out of time and there's just not enough time to do it. So I'll post lecture videos. This gives you time to do it. And then whatever classes you come in and ask questions that are currently related to you. A lot of people hopefully log in, but we'll see who does. Okay? For each of your guys' specific classes, I have 3 stat classes. I will open up a Q&A session for each of you, and you'll find it again in this Confer Zoom. I didn't put that name. Click on the link in Confer Zoom. So let's just take a look at one of my stats classes. I don't have it set up yet. This is Monday and Wednesdays. I will see them tomorrow at 2 o'clock. I'm going to go and make their Conver Zoom right now. In fact, they can see me set it up. I will schedule events for Monday and Wednesday. Okay, it don't want to do it. Maybe because I'm doing Zoom right now. When I finish doing this, I'll do it there. You guys will be able to register that way, okay? I'll check back in a couple hours. I might have to make these videos in the morning for how to do some problems in 9.1 and 9.2. Just to show you what we were looking at in StatCrunch for 9.1. You're looking at stats, proportion stats, one sample. Generally, a lot of them are with summary. In fact, let's say I wanted to do, let's do this on our confidence interval real quick. So on coronavirus deaths in California. I can use the 2 examples I did earlier. I'll do them right now. What values did we have? We found that there were 101 cases where the people have died out of 5,551 observations. If I want a 95% confidence interval, see how it says confidence interval for P? I'm going to click it. So here I had P hat. I want to say it was 01819. Deaths were 101. Cases was 5,551. And went stats, proportion stats, one sample with summary. This will be my successes. This will be my observations. I click on confidence interval. And let's say we want 95%. A 95% confidence interval, it says a lower limit of 0.014678909, an upper limit of 0.02171091. I know I computed those by hand. What did I get? Let's just bring that back up. Zero point 0.01468 matches up with that one. 0.0217106. The last one might be off because of rounding. That's a lot of decimal places. Rounding's taking effect. Notice calculating by hand, computer's getting the same calculation. So we'll make a statement. We are 95% confident that the true proportion of casualties amongst COVID-19 victims is between, and I'm just going to do the 4 decimal places I had earlier, 0.0147 and 0.0217. Oops. When you talk amongst humans, we don't say that. It's between 1.47% and 2.17%. That's kind of how we would say it in real life. When I can, I'll log in and check some more problems with you guys. Until then, peace.